Hey guys. Let's see. Oops. I was thinking, so for a warm up, we can do a couple things. So calculate the limit as x goes to 0, 1 over x. And let's say okay. Yeah, so let's resume at like 5:15. Hey guys. All right, let's go over this. So, wait. Okay, one sec. There we go. So the first two hopefully are pretty straightforward, right? Because this is like f prime of 0, where f of x is like the integral from 0 to x of e to the t squared dt, right? So like just by definition, if you define f this way, then this expression is the definition of taking the derivative at 0 for this capital F, right? So by the fundamental theorem, by the second fundamental theorem, right? This equals just the value of the function inside at 0, right? So this is e to the 0 squared, which is 1. All right. So that's the first one. And then this one is similar, right? This is like, you know, this is f prime of 3 if f is the same thing. So, or if you want to think about it differently, I guess you could say, maybe to just quell any technical annoyances or like deal with any technical annoyances, you could define f, just so it's more manifestly obvious that this is the derivative, you could define f to be like the integral from 3 to 3 plus x. Yeah. Of e to the t squared dt. So, and then that's just going to be, you know, the value of the function inside again at the point in question, right? So that's e to the 9. Okay. And for the last one, so here we would say g is like, yeah, f compose, you know, let's say f compose little g, where little g of x is sine of x, right? So by the fundamental theorem of calculus, I think 2 again, g is, or sorry, capital F, wait. Capital F, so, or yeah, capital F, and then capital F is like, yeah, capital F of x is just the integral from 0 to x, right? Of f of t dt. And this is differentiable on R. So then by the chain rule, g is differentiable on R. And okay, I'm just going to move to a new page. So g prime of x is going to be like f prime of, of little g of x times g prime of x, right? So f prime is just little f, right? Yeah. So this is going to be little f of g of x. So this is little f of sine of x. And then g prime is cosine of x. So yeah. So I think that's, yeah, that's it for for that. Any questions? Or, yeah, I mean, questions either about the warm-up or just in general. Anything you'd like me to talk about?
I had a question about the optional homework one.
Yeah, sure.
Yeah. So like, I think I know like informally like how to prove, or like how to say that it's like not piecewise continuous or not piecewise monotonic.
Mm-hmm.
But like, how do you formally show something that's not the case? That's not the case.
Well, I mean, in that case, you can just say like, okay, like let P be a partition, right? Like the statement that something is, okay, yeah. The statement that something is piecewise, if you just go to the definition of like piecewise continuous or piecewise monotonic, then just like negate that statement, right? That's like what you'd want to sort of justify is true. So the statement that something is piecewise monotonic, like piecewise blank or whatever, right, is that there exists a partition. Whoops. P such that like F is blank on each interval, right? So so if you let P be a partition of what's the interval 0, 1? Or negative 1, 1. Yeah, sorry. So negative 1, 1. Then then you can just say, okay, so some like interval of P contains 0, right? Like, yeah, I think no matter what, it's like if 0, yeah, no matter what, like, yeah, no matter what, P will not be, like, P is neither continuous nor monotonic on that interval. Yeah. So no P can exist, making F satisfy the definition of piecewise continuous or monotonic. Right. Does that make sense?
Yeah. Yeah.
Okay. Yeah. Yeah. Yeah, that problem is, I do think it's like really good to work through it. Yeah. So that's good that you're doing that. Okay. So if there are no other questions, we can do some more exercises. So let's see. Oh yeah. Okay, I think this one's pretty good. So let f be a continuous function on R and define capital F of x equals the integral from x minus 1 to x plus 1 of f of t dt for x in R. Show f is differentiable on R and compute f prime. Okay, so yeah, let's say we'll resume at like 5:35. So let me make some, hold on. Yeah, say 2. All right, yeah, there we go. All right. Let's go over this one. So at first glance, it might not be particularly clear how we can apply the fundamental theorem to this, right? Because we see the variable x kind of shows up in both endpoints, right? So the sort of trick to it is first define, like, let's say capital G to be the integral from 0 to x of f for x in R. Then capital F of x is just g of x plus 1 minus g of x minus 1, right? That's just for all x in R. So this is like g compose like u1 minus g compose u2 if you want to be really careful about it, where like u1 of x is x plus 1, u2 of x is x minus 1. So like clearly, so u1 and u2 are just obviously like differentiable everywhere, and u1 prime is u2 prime. That's just 1 identically. And then g is differentiable by the fundamental theorem of calculus 2 again. So by the sum and chain rules, f prime is like g prime of x plus 1, you know, times the derivative of u1, but that's just 1 minus g prime of x minus 1. Again, the derivative of x minus 1 is just 1. So this is, so f prime, this would be f prime of x, sorry. So f prime of x, right? G prime is just little f. So f prime of x is just little f of x plus 1 minus little f of x minus 1, right? So yeah, any questions about that?
A question, do we need to introduce the u, or can we just like split it up as like f of x is integral from 0 to x plus 1 of f of t dt minus integral from 0 to x minus 1 of...
Yeah, actually, I mean, I guess you could do that. Yeah, and so if you do it that way, you can actually think of it as like, so if you just say like f of x is the integral from 0 to x plus 1 of f minus the integral from 0 to x minus 1 of f, then you could say this is like the integral, let's see, the integral from 0 to x of f plus the integral from 0 to 1 of f minus.
Well, why do we need to do that though? We can
Wait,
just use, you can just differentiate both sides and use linearity of differentiation, and then use FTC on each.
Yeah, but I mean, ultimately, you're still using the chain rule, right? Like by giving names to like, right, because there's, you know, some function, some like non-identity function up here, right? I mean, it is true, like it's kind of trivial what ends up happening, right? Because the derivative of this function is just 1, but technically speaking, as stated, the fundamental theorem sort of only applies to when you actually have x isolated in the bound up here. But yeah, I mean, they're sort of only cosmetically different in the end, ways of using the same argument. Yeah. All right. Anyway. All right. Yeah. Sorry, I was just thinking about something else. Yeah. So I had another. So there was an exercise that I think actually is pretty good to do from the previous section that I was kind of hoping to get to at some point. So I think now is as good a time as any. Let's see. Oh, right. So yeah, let's do this one. So this is exercise 33.9. So let Fn be a sequence of integrable functions on AB, and suppose Fn to F uniformly on AB, prove F is integrable and the integral from A to B of F equals the limit as n goes to infinity of the integral of A to B of Fn. Okay, so what I want to say about this is it might be a little bit confusing when you look at it at first because it looks almost identical to the thing we already proved. And in fact, I think I might have tripped up slightly when I talked about this in lecture. It was a few lectures ago, right? A bit earlier on when we were first talking about uniform convergence, where I proved a theorem that was like, basically it looked the same as this, but instead of integrable, it was a theorem about continuous functions. So it's like if you let Fn be continuous and Fn go to F uniformly on AB, then, you know, F is continuous and the integral from A to B of F is the limit of the integrals of Fn, right? So in that case, basically, yeah, I think I might have said something like, okay, continuity, you don't really need continuity here. It's enough just to have them all be integrable. And I guess it is true, like what we talked about, what we did to prove that theorem works if you actually assume that F is also integrable. But so the real like the most difficult part of this, the most substantial part of this entire problem is literally this part, proving F is integrable, because everything else pretty much like, or this part here follows by basically the same argument we used to prove this version of it. And like the thing is, in this case, right, when we were assuming that all of them, that when we assumed that all the Fn were continuous, then because the convergence was uniform, that actually guaranteed that F itself was continuous, which in turn guarantees that F is integrable, right? But without that bit of logic, then like proving that the limit, the uniform limit of integrable functions is also integrable is like its own thing. It's like a separate thing, right? But then the formula here, like the equation here, essentially ends up following, after you prove this, it follows by like similar reasoning to this thing, which I mean, I encourage you to like remind yourself of how that goes. But this really is like the most important part, is just proving it's integrable. So I'm gonna give you guys another like 10-ish minutes. So let's, oh, whoops. Yeah, let's resume at like 5:55, 5:56. I don't know.
Question?
5:57. Huh?
In the original proof of this, did we ever use the continuity? Like in the proof that of like the one that you showed us in lecture?
I think like we were implicitly using the continuity to argue that the integral of f itself exists in the first place. Because for this to exist, you have to know that f is integrable. And in that context, we hadn't really defined integrability. So we were basically saying that because this f is continuous, this limiting function f is continuous, then the integral automatically exists. So there's no question of whether this equation makes sense, basically.
So basically, all we need to do here is just prove that f is integrable.
Essentially, yeah. I mean, I do recommend that, like that comes first, yeah. And then after that, I would say, you know, reacquaint yourself with how this argument works. But yeah, that's basically the entire problem. Yeah. Okay. Hey, all right. So let's talk a bit about this. It's a little bit complicated. At least I don't know. My approach to this, I don't think that there's any like truly, slick way of making this argument. There are definitely going to be variations. Obviously there's room for some variation here in how you decide to structure the argument, but I think they all will kind of revolve around a similarly complex idea, which is that basically what we're going to do is we will. So the strategy is like construct P such that, so like given epsilon greater than 0, right? Construct P such that U of FP minus L of FP is less than epsilon, right? And we do this by uniformly approximating F by some Fn and finding a P such that U of Fn P minus L of Fn P is less than like some smaller bound, some other bound, right? Something else that we pick, right? Something else that we pick in order to make the ultimate, like using, if you use P, I think you can just use the same partition P, but using some estimation, you can turn this bound that we've enforced for Fn, this bound, you can turn it into a bound for F itself. And ideally, the way we pick this will make it so that this ends up being less than epsilon, right? So I think the first step is like, okay, say like Fn minus F is like less than, epsilon prime for some epsilon prime we've chosen. And then like, let's estimate, and say, or yeah, let's say this is like, I don't know, epsilon 1. And then let's say that U of F n P minus L of Fn P is less than like epsilon 2, right? Let's estimate U of F P minus L of F P, right, in terms of these things. So what we'll have is, right, so U of F P is going to be the sum of like, or yeah, let's say, yeah, sorry, minus L of FP is the sum from K equals 1 to N. And then we'll have like, capital M of F and whatever. I don't want to write all of it out right now. Minus little m of F, right? On the intervals TK minus 1 to TK. I just want to try to keep it relatively clean. TK minus 1, right? And so what you can say is, because of the bound that we have, right, this is like less than or equal to capital M of Fn, etc., plus epsilon 1, right? And this is like greater than or equal to little m of Fn plus, or minus, sorry, minus epsilon 1, right? So overall, this is like less than or equal to the sum from K equals 1 to N of like capital M of Fn minus little m of Fn plus like 2 epsilon 1 and then TK minus 1, right? So if you just split this, if you just sort of distribute this term at these terms, right? Distribute this into here, and then you have a separate, like pull out the 2 epsilon 1 times this thing. This equals the upper sum of Fn on P minus L of Fn on P. And then plus like 2 epsilon 1 times like B minus A. So plus 2 epsilon 1 B minus A, right? So basically if we make this be like, so make this be less than, so this is less than epsilon 2 or whatever, right? So just make this be less than epsilon over 2 and make this be less than epsilon over 2. So choose epsilon 1 to be like epsilon over, actually, yeah, we don't, this can be less than or equal to, it doesn't matter. So this can be like epsilon over 2 B minus A. And then epsilon 2 can be like just epsilon over 2, right? And just like paste those choices back into this argument, right? Then U of Fp minus L of Fp is less than epsilon, right? So so theorem 32.5, if I remember the number correctly, that tells us that F is integrable. Right? Any questions about that?
So just confirming, so the epsilon without subscript is the one that we have to
Yeah.
arbitrary, and then epsilon
Yeah.
1, epsilon 2 we choose.
Yeah, it's like the way I do this is just like my methodology, I guess, that I've, or a habit that I've developed, where it's like I kind of know the outline of like what I'm trying to do, and I know like I have control over two things, right? I have control over how close Fn is to F, and I have control over how fine the partition is. I have control over like the error between the upper and lower sums for any particular Fn I might choose, right? And so like if you think about it like in your head, just the sequence of things that has to happen is like, okay, we first have to like pick the Fn that we want to focus on. So that's going to be based on like how close we think we need it to be to F, right? And then we have to pick P for that Fn based on like how close we need the upper and lower sums to be. But the way we like choose how close we need those things to be to each other is with foresight towards like how much error between the upper and lower sums of F are we going to get based on like the amount of error that we allow for our approximations for Fn, right?
Makes sense.
So it's kind of like what I'm doing is I'm saying, okay, yeah, we will eventually choose this. Like, you know, this is all kind of like what I just did is kind of like this weird hybrid between actually doing a proof and doing scratch work, right? So I sort of working out what the epsilon 1 and epsilon 2 are is basically, you could think of it as scratch work. And then you could go back and actually like write this all out.
The whole proof
Properly, exactly. You could say like, okay, literally just choose Fn so that this is less than epsilon over 2, right? And then choose P so that this is less than like epsilon over 2b minus a, right?
Mm-hmm.
Or vice versa. Sorry, vice versa. Yeah, epsilon 1 is, yeah. So choose n so that this is less than epsilon over 2b minus a, and then choose P so that this is less than epsilon over 2. And then everything will just work out, right? Yeah.
Makes sense. Thank you.
Mm-hmm. Yeah, any other last minute questions? There's going to be a review tomorrow, so there will be more opportunities, obviously. All right. Yeah, so yeah, see you guys tomorrow then.
Thank you.